The demand for DC systems in naval applications has greatly increased in recent years as DC systems are safer and more reliable compared to AC. However, a major flaw exists within DC systems as it is unable to detect and localize arc faults naturally. This highlights a critical defect that must be addressed to prevent dangerous situations that could potentially occur. This project proposes a self-powered design that detects faults existing and transmits the fault data wirelessly.
This design seeks to contain a self-powered network of systems from a 500-volt DC bus that identifies a fault occurring, defines its location, and relays the fault information wirelessly. The design proposed here entails the individual systems required to achieve this function as an arc fault sensor circuit has already been created. Here is an abstract version of the design. A power converter will supply an arc fault circuit along with the wireless communication system from a 500-volt DC bus. The communication system transmits the fault data wirelessly to some remote device. What are the requirements? Well, the power converter must transform from a 500-volt bus input to 3.3 volt in a step-down solution without exceeding 5 watts on the load. The wireless communication system must be able to relay the fault data wirelessly with a 10 millisecond latency. A flyback converter was implemented as the power converter needed to supply the subsequent systems in the proposed design given its simple topology. The schematic for multi-spice was used as the reference model when the physical converter was built and tested. The flyback converter operates with a switching frequency of 200 kHz and a duty cycle of 12%. The communication chip used draws 25 mA at 3.3 volts, therefore to represent this a 25 mA current source load was attached. This is also the same as setting the load to 132 ohms. But what about the transformer? The transformer has a turns ratio of 150:1. It was constructed using an RM10 core size, 150 turns on the primary with 28 gauge wire, 1 turn on the secondary with 14 gauge wire, and a magnetizing inductance of approximately 87 millihenries. However, the transformer resonates before the switching frequency. It has a parasitic capacitance of around 48 picofarads. Given the low specifications, we were unable to prevent resonance. When simulated, the converter generates the following waveforms. The top graph exhibits the converter successfully outputting 3.3 volts. The flyback converter was tested and compared with its simulated iteration at 500 volts. An electrical load was connected to the output terminals of the board and set to 132 ohms. Here's the comparison of the simulated and measured waveforms at 500 volts. The drain to source voltage in both graphs are very similar, each being at around 1.06 kilovolts. However, there's a 500 millivolt discrepancy between the output voltages, where the load measured around 2.8 volts drawing 20 milliamps. The gate-to-source voltages are around 10 volts for both waveforms.
Latency was determined by toggling a pin in the receiving ESP's code for processing received data and recording the time between them. From this we found we had latency ranging from 667.5 microseconds to 13.4 milliseconds, which doesn't meet our expected max time of 10 milliseconds.
Using a waveform generator to simulate the output of the arc fault sensor, the entire system from the comparators to the PC output was tested. We can see in the image that when the waveform indicated by the light blue surpasses 1.8 volts, the output of the comparator indicated by the dark blue also reacts appropriately. The PC output also responds, determining the fault.
The combined solution is the amalgamation of the wireless communication system solution, some of the detection system, and the power converter solution. On the final PCB, the power converter supplies the ESP and comparator with 3.3 volts on a path shown with the orange arrows. And the arc fault detection output can be attached to the connect arc fault detection circuit output here via to be input into the comparators where the red arrows are. The ESP's antenna relays the arc fault wirelessly to display on a PC. The push-in programmer and programming instructions make reprogramming easy for a future senior design team that takes on this project.
The flyback converter created a 500 millivolt discrepancy from its intended requirement voltage of 3.3 volts, only outputting 2.8 volts at 500 volts regardless of the duty cycle. The converter successfully dissipated less than 5 watts across the load, resulting in only 60 milliwatts of power being dispersed.
Wi-Fi had a tested maximum latency of 13 milliseconds, not 10 milliseconds. Nevertheless, the detection and communication system was able to successfully transmit fault data.